Our first speaker today is Gauthier Raimondi, who's going to tell us about type-directed program transformation for constant time enforcement. All right, Gauthier.
Yeah. Do you hear me well?
Very good.
Okay, great. Just sharing the screen. Okay. Thanks, firstly. And hello, everyone. Today I will talk about our current work with Frédéric Besson and Thomas Jensen about type-directed program transformation for constant time enforcement. So firstly, I will try to put some context and try to define what do we mean by constant time. To do so, I'll first define what a timing attack is. So timing attack is a kind of sub-channel attack where the attacker tries to deduce secret information by analyzing time information of the system or the program. We say that time leaks information on secret if the behavior of the program is dependent of the value of the secrets. For example, if we have a conditional jump on a secret value, sorry. If we have two branches of a conditional, we will have a different execution time. Just analyzing the execution time of the global program will give us access to the value of the conditional. And if the jump is on a secret value, it will give us access to the value of some secrets. It's actually the same for array accesses. If we make an array access on a secret value, we can, by using some cache-based timing attack, obtain the value of the secret. Such attacks were proved practical back in 2005 by Bromley and Bonnet, who succeeded to extract private keys from an OpenSSL web server using remote timing attacks, but they have been used many times since then. To counter these types of attacks, one of many solutions is to use a new programming policy, constant time. So this programming policy is to defend the implementation against the timing attacks, not the algorithm. I mean, if an algorithm is ill-conceived, it is ill-conceived, even if it is a good implementation. So to do so, we transpose the previous limitation into constraints. So we forbid any control flow decision using secret data and any memory access using secret data as index. For example, if we have a simple program where we have a condition on a secret and then memory access on another secret, we have two forbidden action, and the program is therefore not constant time. Usually, we will transform those conditional and secret into bitwise operation, and thus because we are forbidden to use one of the basic brick of programming, constant time programs are often both hard to write and to maintain. But how to be sure that the program is indeed constant time? We have mainly two ways to do that. We can either verify it or enforce it, and whether at the source or at assembly level. So what do I mean by verify it? It's just that we suppose we have a formal model and we apply it on our code, which can be a source code or compiled code. And enforce is we have non-constant type code, and we guarantee that after a certain number of steps or transformation, we obtain a constant time result. One of such tool to obtain constant time is fact. So fact is a domain-specific language to write constant time code, which means it falls into the enforcer at the source level category. We give the tool a non-constant time source code, and if the initial source code satisfies a certain number of criteria, it will compile it to constant time results. So to identify the subset of transformable program, fact uses an information flow type system, and then applies a transformation based on two main mechanisms. The first one is if conversion, on which I will come back a little more later, and the second is return deferral, which is just a simple mechanism to ensure that there is no return within a sequence context. Because if there was one, obviously the execution time would be different depending of the secret. And yes, as I said earlier, fact ensures that after the transformation and without compiler optimization, the program is indeed constant time. Based on fact, our goal for this work were to allow more programs, to be transformed than fact was is able to. And to do so, we have to define a more permissive information flow tracking type system, which would authorize and accept more programs, but still rejects any we aren't able to transform, or just which aren't constant time by definition. Then once we have a class of transformable program, or at least program we accept, we propose a type-directed semantic preserving transformation on those program based on here two main mechanisms: delayed if conversion, which is an upgraded version of the facts in conversion, and scope increase, which is a twist or tweak to this if conversion. The final step is to implement this transformation into Jasmine as an early pass. So Jasmine is a secure compiler which does have a constant time preserving property. And the goal here is to take a non-constant time source code, transform it into constant time source code, and then compile it all the way using the Jasmine compiler. So to do all this work, we first need to define the language on which we will work. So to do so, we selected a common subset language between fact and Jasmine. So just a simple language with arrays and a for loop. Two things are to be noted on this language. First, we annotate our conditions to identify them using program points. So that's just a positive int or classic, which are unique on each condition. And secondly, we have a conditional expression. So the result we expect from this conditional expression is just the usual conditional expression, just as is C. However, the evaluation of it is a bit different. We actually start by evaluating the two values, E2 and E3, and then only then we evaluate E1 and choose the reason accordingly. So in practice, such an expression and operation could be implemented using bitwise operation or a CMOV, depending of the architecture or the developer's will. And to reason and formalize more this language, we define leakage semantics on it. So we say that leakage is generated when we evaluate a conditional or when we perform an array access. So that allows us to track the possible leaks of our programs and where those secrets could leak. What's interesting is that by construction, our conditional expression does not leak the value of E1 because we always execute both E2 and E3. So we always have the trace of E2 and E3. We cannot deduce the value of E1 from only this portion of code. And using this leakage, we are also able to define the constant time property more precisely. So a program is constant time if for equivalent static environment, meaning environment which are which differ only on secret values. The execution are indistinguishable for an attacker observing the trace of liquid events. For example, okay, if we take a kind of simple example with just a secret condition, and in one branch conditional expression and the other just an assignment, then the trace of leakage would be the value of the conditional, here S, then the sequence of the leakage of the two branches. Here we don't have to worry about the L branch because it's just an assignment of public values, but the then branch is a conditional expression where each value is a memory access. So we leak both the array and the index. So our final leak is S T0 T1. And because we have S in our leak and obviously the secret is dependent of the secret, this program is not constant time. So how does fact really transform a non-constant time program like this into a constant program? So as I said earlier, the first mechanism is the if conversion. So if conversion is in the essence a pretty simple transformation which generates branches and predicated code from a condition. So if we have, for example, just a simple condition with two assignments of low values, sorry, then it is transformed into two conditional expression. In the first one, we basically say if s, then x is equal to e1, and in the second, if not s, x is equal to e2. So we obtain the same semantics at the end. However, what's interesting is that we always execute the same expression, so no difference in the trace leakage. And we turn indirect flows into direct flows explicitly by using the conditional expression. So to accept and identify programs on which fact can do this if conversion, it uses a type system. So the type system aims to accept transformable programs, as I said just earlier. And for so, it uses a flow intersensitive type system, which allows conditional to branch on secret because it will be able to transform it away anyway. However, it still disallows memory accesses on non-public values, even if the secret characteristic of the variable is because we are inside a private security context. So to actually upgrade and improve the class of transformable programs, we had to define our own type system. So we did so with the ID, well, the main ID that we want to introduce leakage on direct flow only. What this means is that if we have a variable which is private by an indirect flow, then we don't really care if it's leaked away because we suppose we will be able to transform it and not leak anymore. So to do so, we add a flow sensitive type system to effectively track the indirect flow. And we extended the usual ILO lattice with a new type, indirect of S, where S is a set of program points where each program points identify a condition. So basically, if we have variables which type is indirect of S, that means that this variable is secret by dependency into each condition contained in the set S. And if we actually want to type something using this type system, we need two main variables. Firstly, kappa, which is a security context. For example, if we enter a secret condition P, then kappa will be augmented by P, and gamma, which is a classic typing environment. So, for example, I will present here a code snippet that I will use during the rest of the presentation. So we have a condition as annotate P, and in the then branch an affectation on the public values, and then narrow access on the X we just assigned, and in the else branch the same memory access without the assignment prior. So if we define an initial typing environment gamma where S is high and every other variables is low, what's interesting is that after the first assignment x is equal to y, we obtain that x is actually indirect of p instead of the classical I, and that allows us to accept the memory access because we suppose we can transform indirect flow away and delete the potential leakage. So how do we actually transform the leakage? The first thing to note is that this example is not typed by fact for a really simple reason. The assignment is x is equal to high would type x high because we are in a security context. So the memory access just after would be completely rejected. And it does so not without any reason, because if we apply the naive if conversion on this code, we would obtain that X is secret just after the first affectation because we would introduce an direct flow, so we don't have the right to make a narrow access on this variable. So how can we actually transform this code into constant time? It's quite simple in the ID. We delay the if conversion and the introduction of direct flows at the cost of additional variables. So if we still take the same example, the first step would be to introduce additional variables in both branches and rename the block. So here we would introduce xn, xelse, rzen, and relse, and just rename in the according block. This allows us to kind of execute both branches in parallel. And the next step is to actually merge the branches. So first we delete the condition, we put the block of the branches in a sequence just after the initialization of the variables, sorry. And finally, we merge using our conditional expression. And if we take some time to look at the result code, we can see that all memory accesses are done before we introduce secrets, and even more so before we introduce any direct flow. So we don't have any leakage anymore. Whatever the value of S is, we will leak xn and xelse, and that's all. However, this transformation is still not enough, because if we take the previous example and we just take the memory access out of it, then the information about the indirect flow is not remembered long enough to handle the memory access. And if we try to apply the naive transformation, we would obtain a code in which we will introduce the indirect flow as by the mean of conditional expression before we can try to transform the memory access, and such we will leak X and S. So to actually counter that, the idea is to put everything that is problematic inside the condition. So we call this the leaking continuation, which is really just the maximal block where we can see leakage due to the condition P. And we put this leaking continuation in both branches of the condition. So that does not change the semantics because we just moved code innocently. And in this example, we just obtained the previous example in which we have already shown that we can transform it away. So we can transform transform this resulting code into constant time completely. However, even if we move code around, we are still in the end doing some if conversion, and if conversion has a primal flow. That is, it can introduce out of bounds error. Indeed, if we at any time have a memory access which safety is dependent of the value of the condition within it is. So for example, here we have an access at the index I, and we can suppose that this access is only safe if y is inferior to s. When we will apply the if conversion, even the delayed if conversion and with the scope moving, we will always make the access to the index I, and we could introduce out of bounds error. So the way facts handle this is by adding a static condition into its type system, which should be provable using only public available information. So without using condition which are secret or anything secret actually. However, we wanted to do it dynamically, so we just add redundant dynamic checks into the code, into every memory access. So by just checking that the index is within the bounds or else accessing to the zero index, for example, we preserve the semantics in the initial program because we suppose the initial program is safe. And because the access are always safe, because we check, the safety is preserved in the transform program. So the question would be, what happened when we are outside of the bounds. So in case of an affectation to an array, we just affect the index 0 to the index 0, so it's just a dummy operation. And if we just try to retrieve a value, actually it won't matter, because as a merge step, we will discard the value anyway. So we can store whatever we want, and that doesn't matter. So at the end, our transformation is composed of multiple steps. The first one is to choose the outmost last secret condition. So the outmost criteria is just here to avoid any imbricated ifs or nested if, because it could be quite a pain in the ass to handle. Then we rewrite it using scope increase, that is moving the leaking continuation back into the condition. And then we can dumbly apply the public safety countermeasures and the classic if conversion, well, delayed if conversion, and we do that while we have secret condition. So at the end, we seems to have a broader class of transformable programs than fact, with a type system to identify them. A semantic preserving transformation into constant time. Also, if we note that we only check constant time a posteriori using a type system. However, we still have some limitation in ongoing work, mainly that because of our language restriction, we don't have any returns, even though we suppose we could insert the same method as fact quite easily into our system. And there is two more things quite problematic. First, scope increase isn't actually that easy, because when we move non-leaking accesses, we introduce indirect flow. And secondly, we still haven't have any formal proofs. We are still well, testing and checking that it works, and believing blindly. So that's it, and thanks for listening.
All right, thank you. Okay, so as usual, we will take questions online through the Q&A tab. So listeners, please go ahead and post your questions. In the meanwhile, I had one question, which is, can you go back to slide 7?
Sure. Oops, missed it. Yeah.
Yeah, so you say E1 question mark E2 colon E3 does not leak the value of E1.
Yeah.
And that, I was a little surprised by that. Shouldn't it be the case that this is semantically equivalent to an if in terms of execution trace and reduction semantics?
No, that's the whole point of the whole point of the construction, is that we do not leak the E1. We implement it in a way where it does not leak. It does not leak.
Okay, so this is like really a new primitive construct.
Yeah. We
Okay,
just uses the same syntax, but that's anything.
Okay, I got confused by the syntax. I just thought that was okay.
Yeah.
Good. All right, so we have a first question online from Akram.
I'm assuming you allow for follow-up expression as an else expression. Did I add? I'm not sure I quite understand the implication.
Akram, if you want to interact with the speaker, you can use the raise hand feature, and then you'll like get a chance to talk and clarify your question if you choose to do so.
Okay.
Hello, can you hear me?
Oh
Yes.
yeah.
Oh yeah, cool. Yeah, so I was thinking about the transformation where you sort of execute both the then and the else branches, and then basically like choose the correct effect based on the if condition. So I was wondering, like, if the then branch is just like complicated, like if it's a for loop that contains memory updates, how do you actually do this without and without like basically updating the memory incorrectly Like, do you have to
Oh, yeah.
unroll group and then like introduce temporary variables for all of the iterations? How do you do that?
Well, when it's just a memory modification on a variable, we just introduce temporary variables that we will discard at the end.
Right.
But when it's in an array or something, we actually have a bit of a construction where we only update if we have if we are in the right path. So here, well, when we are updating array, we are introducing direct flow. I indeed did not speak about that, but we are introducing direct flow.
Yeah.
Well, t of x is equal of if s t of x else well, t of x is equal if s 0 else t of x, for example.
I see. Yeah. Yeah.
So yeah, okay.
Yeah. Got it.
All right. Well, let's thank the